Guys, we're looking at some more of our two-stage blower operation where we're retrofitting it. Theoretically, you have a motor in place for a single speed system. You come back and want to add a two-speed system. This is sort of our little mad scientist part two from the first one we did a couple weeks ago. If you see in the picture, we have an IFC integrated furnace controller with a cooling tap and a heating tap. We can sort of ignore the heating tap. It's just there to show us that there's going to be two taps on these boards, one for your cooling tap for your PSC motor, one for your heating tap. Typically, the heating tap is a lower speed, although it doesn't have to be. In some instances, it may be higher, but for this case, we're going to go with the typical, which is a lower speed. We can see that the two taps go over. One goes directly to the indoor fan motor, the heating tap on low. The other one's going to go to a relay that we're going to install. Typically a 9340 relay is what I like to use, nice and reliable. Tested over time. It's been around for a long, long time. We'll have a coil on the bottom of it that has a Y2 and a common to energize the coil. If you look up on the top, you have the cooling tap, which is 120 volts going into the first terminal. On top, you have a normally open, which means it does not have voltage when the coil is not energized. That's going to high speed. You have a normally closed, which is energized when the coil is not energized, going to low medium speed. I'm using a 4-speed motor. Could be 3-speed, could be 5-speed, could be any amount of speeds. If you have a 2-speed motor, you might have to do a little bit of more figuring because you're going to be using the heat speed for two different things. So we're going to use a motor that has enough taps to produce a heating, cooling 1 and cooling 2, or cooling low and cooling high. If we look back at the relay, we are normally closed between the cooling tap and it goes directly to low medium. That's going to be our first stage of cooling. If the Y2 gets a call from the thermostat, it's going to energize the coil. It's going to cause the relay to switch from normally closed to normally open. So it's going to pass from the cooling tap to normally open and switch the blower speed to high. So once the compressor goes into high cool, our blower will go into high speed. Keeping in mind that this is an example, you're going to want to verify and get the airflow as close as possible. One of the flaws with the plan is that the airflow won't be designed from manufacturer, so you're going to have to match it up to what you think it should be based on the manufacturer settings for the 2-speed unit. There is a very real possibility that you won't be able to match them up as closely as you would like. With more speed taps on a motor, you'll do a better job of it. But if you have a motor, let's say you have a 3-ton system that runs 1200 CFM, and then on low speed it runs 700 or 800 CFM, you may or may not be able to achieve that particular CFM. You can come close, more than likely, but you probably won't be right on target. You can probably get your high speed right on target, or your cooling too, but your low speed may be a little off. That's what I would presume would happen in this situation. Your low speed will be the one that's less likely to be exact. That is a PSC motor being retrofit to become a 2-stage motor for a new 2-stage cooling system. And we're going to look at one alternative way to use an aftermarket X13 motor for the same purpose. As you can see, we have a similar drawing to up top. We have our relay, we have our indoor fan motor, we have our cooling tap. We kind of ignored the heating tap this time so it wouldn't be too cluttered. But as you see, we added a transformer. You see TFR as transformer. We have our cooling tap powering the transformer, the other leg going to neutral. It's 120 volts, to 24 volts. On the low voltage side of the transformer, or the secondary side there on the right, we have a R hot on top, and you have the common on the bottom. And you see the common's going to go to the indoor fan motor, which is an X13. X13 will have 2 plugs. We'll have a speed plug, and we'll have plugs for the high voltage power, the ground, and the common low voltage. So we have our common running over there to that part of the indoor fan motor plug. On the left side of the indoor fan motor, we have all of our speeds. I have 5 listed. Doesn't necessarily mean there'll be 5. That's what we're using. So instead of switching high voltage between cooling tap, normally open, normally closed, we're switching low voltage. Our cooling tap, which used to produce 120 for the PSC blower is now producing 124 transformer, which is producing 24 volts, so it can power the ECM motor or get it started. So let's say we'll have 24 volts on hot going to the cooling tap side of the relay. Normally it will be going to normally close, which is medium low or low speed cooling. When we get a Y2 call, our relay will switch to normally open and go to high speed cooling. Again, you may have to tamper with this to get the right airflow. This is just an example. And this is one way where you can use the original controls and add on a couple items so that you can use a 2-speed cooling system. Theoretically, you'll probably sell a 2-speed controller inside of a brand new furnace and change out the whole thing. But this is sort of a Frankenstein theoretical and just a way to get familiar with using relays to do different things and sort of getting your brain thinking. So what do you guys think of it? The good, the bad. There's lots of versions of this. You can probably come up with a few alternatives to this. It's just a kind of an exercise to get your brain going. So when you're out in the field and you need to solve a problem, you can use some of these out-of-the-box ways to solve them. So